warahmatullahi wabarakatuh. Hello everyone. Today we will explain about point multiplication and projection of vector. Firstly, let me introduce ourselves. Firstly, it's me, Nurlaila Ramadhani, with name 2202931, and then my friends
Selvia Salsabila with name 22029104.
Puja Islami Putri with name 22029088. Difa Sepri Wahyuni with name 22029128.
Abdul Furqan with name 22029054.
There are three topics will be explained with Selvia Salsabila. The first topic is dot product, the second topic is component of the dot product, and then the third one is algebraic properties of the dot product. To Selvia Salsabila, time is yours.
The first topic is dot product. Let U and V be non-zero vector in two-dimensional space or three-dimensional space that have been positioned so that their initial points coincide. We define the angle between U and V to be the angle theta determined by U and V that satisfies the inequalities theta greater than or equal to 0 and theta less than or equal to pi. This is the figure of the angle theta between U and V satisfies theta greater than or equal 0 and theta less than or equal to pi. Definition of dot product. If U and V are non-zero vector in two-dimensional space and three-dimensional space, and if theta is the angle between U and V, then the dot product of U and V is denoted by U dot V and is defined as U dot V equals the length of a vector U times the length of a vector V times cos theta. If U equals 10 or V equals 10, then we define U dot V to be 0. The sign of the dot product reveals information about the angle theta, which we can obtain by rewriting formula U dot V equals the angle of a vector U times the angle of the vector V times cos theta, as cos theta equals U dot V over the length of a vector U times the length of a vector V. Sin theta greater than or equal to 0 and theta less than or equal to pi, it follows from the above formula and the properties of the cosine function studied in trigonometry that the first one, theta is acute if U dot V greater than 0. The second one is theta is obtuse if U dot V less than 0. The last one is theta equals pi over 2 if U dot V equals 0. Example of dot product. Find the dot product of the vector shown in figure. Solution. The length of the vector U equals 1 and the length of the vector V equals 2 times square root of 2. And the cosine of the angle theta between them is cos 45 degrees equals 1 over square root of 2. Thus, it follows from formula that U dot V equals the length of U times the length of V times cos theta. We substitute the length of the vector and the cosine of the angle theta. So, we got 1 times 2 times square root of 2 times 1 over square root of 2. So we get U dot V equals 2. The next topic is component from of the dot product. Let U equals U1, U2, U3, and V equals V1, V2, V3, be two non-zero vectors. If as shown in figure, theta is the angle between U and V. The law of cosine yields the length of a vector PQ squared equals the length of a vector U squared plus the length of a vector V squared minus 2 times the length of a vector U times the length of a vector V times cos theta. Sin the length of a vector PQ squared equals V minus U. We can rewrite as the length of a vector U times the length of a vector V times cos theta equals the length of a vector U squared plus the length of a vector V squared minus the length of a vector V minus U squared over 2. Or U dot V equals the length of a vector U squared plus the length of a vector V squared minus the length of a vector V minus U squared all in bracket over 2. We substituting the length of a vector U squared equals U1 squared plus U2 squared plus U3 squared. And we substituting the length of V squared equals V1 squared plus V2 squared plus V3 squared. And the length of a vector V minus U squared equals V1 minus U1 squared plus V2 minus U2 squared plus V3 minus U3 squared. We obtain after simplifying U dot V equals U1 times V1 plus U2 times V2 plus U3 times V3. So we can call it the 15th formula. The companion formula for vector in two space is U times V equals U1 times V1 plus U2 times V2. So we can call it the 16th formula. Modified by the pattern in formula 15 and 16, we make the following definition. Definition of component from of the dot product. If U equals U1, U2 until Un and V equals V1, V2 until Vn are vector in n dimensional space, then the dot product of U and V is denoted by U dot V and is defined as U dot V equals U1 times V1 plus U2 times V2 plus until Un times Vn. Example of calculating dot product using components. Use formula 15 to compute the dot product of the vector U and V in figure. Solution. The component from of the vector are U equals 0, 0, 1 and V equals 0, 2, 2. U dot V equals U1 times V1 plus U2 times V2 plus U3 times V3. We substitute U and V in the formula. So we got U1 equals 0 times V1 equals 0 plus U2 equals 0 times V2 equals 2 plus U3 equals 1 times V3 equals 2. So we got U dot V equals 2. The next topic is algebraic properties of the dot product. In the special case where U equals V, we obtain the relationship V dot V equals V1 squared plus V2 squared plus until Vn squared equals the length of a vector V squared. This yields The following formula for expressing the length of a vector in terms of a dot product. The length of a vector v equals the square root of v dot v. Dot product have many of the same algebraic properties as product of real numbers. Theorem 3.2.2. If u, v, and w are vector in n-dimensional space, and if k is a scalar, then the first theorem u dot v equals v dot u, it's called symmetry property. The second theorem u dot v plus w all in bracket equals u dot v plus u dot w. It's called distributive property. The third theorem is k times u dot v all in bracket equals k times u all in bracket dot v. It's called homogeneity property. The last theorem, v dot v greater than or equals 0 and v dot v equals 0 if and only if v equals 0. It's called positivity property. Okay, now we will try to prove it. The first one, let u equals u1, u2 until un, and v equals v1, v2 until vn, then k times u dot v all in bracket equals k times u1 v1 plus u2 v2 equals until un times vn all in bracket equals k times u1 all in bracket times v1 plus k times v2 all in bracket times v2 plus until k times un all in bracket times vn equals k times u all in bracket dot v. The second one, the result follow from part A and B of theorem 3.2.1 and the fact that v dot v equals v1 times v1 plus v2 times v2 plus until vn times vn equals v1 squared plus v2 squared plus until vn squared equals the length of a vector v squared. Theorem 3.2.3. If u, v, and w are vector in n-dimensional space, and if k is a scalar, then the first theorem is 0 dot v equals v dot 0 equals 0. The second theorem is u plus v all in bracket dot w equals u dot w plus v dot w. The third theorem is u dot v minus w all in bracket equals u dot v minus u dot w. The fourth theorem is u minus v all in bracket dot w equals u dot w minus v dot w. The last theorem, k times u dot v all in bracket equals u dot k times v all in bracket.
We will show how theorem 3.2.2 can be used to prove part B without breaking the vector into component. Prove u plus v all in bracket dot w equals w dot u plus v all in bracket. Using distribution properties, we get w dot u plus w dot v. Using symmetry properties, we get u dot w plus v dot w. For example, u minus uv all in bracket dot 3u plus 4v all in bracket equals u dot 3u plus 4v all in bracket minus 2v dot 3u plus 4v all in bracket. Or we can write it to be
3 times u dot u plus v times u dot v minus 6 times v dot u minus 8 times v dot v. We get 3 times the length of u squared minus 2 times u dot v all in bracket minus 8 times the length of a vector v squared.
Next is topic that will be explained with Difa, Sepri, Wahyuni. There are 4 topics will be explained with Difa. The first one is Cauchy squares inequality and angle and dimensional space. The second one is geometry in n-dimensional space. The third one is dot product as metric multiplication. And then the fourth topic is a dot product view of metric multiplication. To Difa, Sepri, Wahyuni, time is yours.
Okay, I will explain about Cauchy square inequality and angle in n-dimensional space. The inequality for sums was published by Agustinus Cauchy 1821. The corresponding inequality for integrals was published by Victor Bunyavkovsky 1859 and Hermann Square 1888. Square gave the modern proof of the integral version. The theorem about Cauchy square inequality, if we have two vectors, it is vector u and vector v. If u equals v1, v2 until vn, and v equals v1, v2 until vn are vectors in n-dimensional space, then the absolute value u dot v is less than or equal to the length of u dot the length of v. Or in terms of components, u1, v1 plus u2, v2 plus until vn is less than or equal to u1 square plus u2 square plus until vn square out in bracket 1 to the power of 1 over 2 dot v1 square plus v2 square plus until vn square out in bracket to the power of 1 over 2. Okay, I will explain about the proof of Cauchy square inequality formula. The inequality states that the absolute value of the dot product between the absolute value x dot y is less than or equal to the length of x dot the length of y, where vector x and vector y is not 0. Example, we have vector z is equal the unit vector in the x direction minus the unit vector in the y direction. Now, the unit vector is the vector itself divided by magnitude. So we can write vector x over the length of vector x minus vector y the length of over the length of vector y. If it is still element of n-dimensional space. Now I am going to take the product between z and itself. So we can write vector z dot vector z equals x hat minus y hat all in bracket dot x hat minus y hat in bracket. Right side we can simplify by distributive dot product. We can write z dot z equals x hat dot x hat minus x hat y dot y hat minus y hat dot x hat plus y hat dot y hat. The length of vector z square equals the length of x hat square minus 2 dot x hat dot y hat plus the length of y hat equal the length of y hat square. We know the magnitude of the unit vector is equal 1, so we can write the length of vector z square equals 2 minus 2x hat dot y hat is greater than or equal to 0. Right side we can simplify divided by 2, so we get 1 greater than or equal to x hat dot y hat equals x over the length of x dot y over the length of y equals 1 over the length of x dot the length of y equal dot y. So we can get the result is the absolute value x dot y is less than or equal to the length of x dot the length of y. Okay, next material I will present about geometry in n-dimensional space. Here are two fundamental theorems from plane geometry whose validity extends to n-dimensional space. The first one is the sum of the lengths of the side of a triangle is along at least as large as the third. Look at the picture. In this picture we have one triangle. In triangle we have three sides. One side is u, two side is v, and third side is u plus v. The second one is the shortest distance between two points is a straight line. Look at the picture. In the picture we have one triangle. In triangle we have 3 points. One point is u, two point is w, and then third point is v. The theorem about geometry in n-dimensional space. If we have three vectors, vector u, v, and w, and then we have two theorems. The first one is the length of u plus v is less than or equal to the length of u plus the length of v is triangle inequality for vectors. The second one is du dot v is less than or equal to du dot w plus w dot v is equal to triangle inequality for distance. We can prove this formula. Formula 1 we can prove is the length of u plus v square equals u plus v dot u plus v equals u dot u plus u dot v plus v dot v equals the length of u square plus u plus 2u dot v plus the length of v square. We know u plus v is orthogonal, so u dot v equals 0. We get the result is the length of u plus the length of v all in bracket square. This completes the proof signs, but sides of the inequality in part A are non-negative. And then we can prove formula B. U dot v equals the length of u minus v equals u minus w plus w minus v equals d u dot w plus d w dot v. It is proved in plane geometry that for any parallelogram, the sum of the squares of the diagonals is equal to the sum of the squares of the four sides. Look at the picture. In this picture, we have one parallelogram. In parallelogram, we have four sides and two diagonals. The theorem about parallelogram equation for vectors. If u and v are vectors in n-dimensional space, then the length of u plus v squared plus the length of u negative v squared equals 2 times the length of u squared plus the length of v squared all in bracket. We can prove this theorem. The length of u plus v squared plus the length of u negative v squared equals u plus v dot u plus v plus u minus v dot u minus v equals u times u dot u plus u times v dot v is equal to u times the length of u square plus the length of v square on bracket. And then the last theorem is if u and v are vectors in n-dimensional space with the Euclidean inner product, then u dot v equals 1 over 4 the length of u plus v square negative 1 over 4 the length of u minus v square. The next topic about dot products as metric multiplication. There are various ways to express the dot product of vectors using metric matrix notation. The formulas depend to whether the vectors are expressed as row matrix or column matrix. There are four types. The first one is U a column matrix and V a column matrix. The dot product is U dot V equals U transpose V equals V transpose U. The second one is U a row matrix and V a column matrix. The dot product is U dot V equals UV equals V transpose U transpose. The third one is U a column matrix and V a row matrix. The dot product is U dot V equals VU equals U transpose V transpose. The last is U a row matrix and V a row matrix. The dot product is U dot V equals UV transpose equals V U transpose. If A is an n times n matrix and U and V are n times 1 matrix, then the follows from the first row in table 1 in the result formula U dot V equals U dot A transpose V and U dot AV equals A transpose U dot V. For example, verifying that A U dot V equals U dot A transpose V. We have three vectors. One vector is A equals 1, negative 2, 3, 2, 4, 1, negative 1, 0, 1. And then vector U equals negative 1, 2, 4. Then vector V equals negative 2, 0, and 4. The first, we can multiply A and U. So we get the result is 7, 10, and 5. And then we can transpose matrix A and then we multiply it by vector V. And we can get the result is negative 7, 4, and negative 1. From which we obtain A U dot V equals 7 and then U dot A transpose V equals 7. The above formula is proven because the results are the same. The next topic about a dot product's view of matrix multiplication. Dot products provide another way of thinking about matrix multiplication. Recall that if A equals Aij is an M times R matrix and B equals Bij is an R times N matrix, then the Ij entry of AB is AI1B1J plus AI2B2J plus until AIRBRJ, which is the dot product of the one row vector of AI1, AA2 until AIR, and the J column vector of B equals B1J, B2J until BRJ. Thus, if the row vectors of R1, R2 until Rn, and the column vectors of B are C1, C2 until Cn, then the matrix product AB can be expressed as AB equals R1.C1, R1.C2 until R1.Cn, R2.C1, R2.C2 until R2.Cn, Rm.C1, Rm.C2 until Rm.Cn.
Next, the topic will be explained by Abdul Furqan. This topic is orthogonal factors. To Abdul Furqan, time is yours.
So the first one is orthogonality. Orthogonal vector is two non-zero vectors U and V in n dimensional space are said to be orthogonal or perpendicular if U dot V is 0. We will also agree that the zero vector in n dimensional space is orthogonal to every vector in n dimensional space. So we say that two vectors are orthogonal if they are perpendicular to each other. And then the dot product of the two vectors is 0. So for the example, so that u equals minus 2, 3, 1, and 4, and v equals 1, 2, 0, and minus 1 are orthogonal in 4-dimensional space. So how to solve it? The vectors are orthogonal since u dot v equals minus 2 times 1 plus 3 times 2 plus 1 times 0 and 4 and plus 4 times minus 1 is equals 0. And the next example is check whether the vectors a equals I plus 2g and b equals 2i minus g are orthogonal or not. For checking whether the two vectors are orthogonal or not, we will be calculating the dot product of this vector. A times b equals 1 times 2 plus 2 times minus 1. A dot b equals 2 minus 2. A dot b is equal 0. Hence, as the dot product is 0, so the two vectors are orthogonal.
Next topic will be explained with Puja, Islami Putri. This topic is lines and planes determined by point and normals. To Puja, Islami Putri, time is yours.
Okay, in this section, I will explain about lines and planes determined by points and normals. One way of specifying slope inclination is to use a non-zero vector and called a normal. That is orthogonal to the line or plane. I will show you a picture. In this first picture shows the line through the point P0, x0, y0 in bracket. There is normal and equals a, b. And the second picture shows the plane through the point P0, x0, y0, z0 in bracket. There is normal and equals a, b, c. The both line and the plane are represented by factorization, that is n times the factor of p0p equals 0. The factor of p0p can be expressed in terms of component r. For the line, the factor of p0p equals x minus x0, y minus y0 in bracket. Thus, formula polynomial form of a line, then a times x minus x0 in bracket plus b times y minus y0 in bracket equals 0. And for the plane, the factor of p0p is equal to x minus x0, y minus y0, z minus z0 in bracket. Thus, the formula polynomial form of a plane, then a times x minus x0 in bracket plus b times y minus y0 in bracket plus c times z minus z0 in bracket equals 0. So, here are some theorems. The first one is if a and b are constant that are not equal to 0, then an equation of the form ax plus by plus c equals 0 represented a line in two-dimensional space with normal and equals ad. And the second one, if a, b, and c are constant and not a 0, then an equation of the form ax plus by plus cz plus b equals 0 represented a plane in three-dimensional space with normal and equals a, b, c. Then we will try to prove the formula. One learned in analytic that line in two-dimensional space is determined uniquely by its slope and one of its points, and the plane in three-dimensional space is determined uniquely by its inclination and one of its points. Let's start with a picture. So here we have a 3D coordinate system. This is going to be x, y, and z. And let's draw a point somewhere in this region. We have a point in this point. We can call it point P0, and we have a vector that is perpendicular from the point, and we can call the vector is n. And we are going to have a position vector that starts from the origin to point P0, and we can call this R sub 0. And here we have another point in this point. We can call the point is point P. We have another position vector start from the origin to the point P, and we can call it the vector is R. So we know we have another vector from P0 to P, and we can call the vector is R minus R0. Then the vector of P0P is equal to R minus R0 because n is perpendicular of R minus R0. Then n times R minus R0 in bracket equals 0 is the same with n times the vector of P0P equals 0. Why? Because we know the vector of P0P is equal to R minus R0, where the n is ABC, the P is XYZ, and the P0 is X0, Y0, and Z0. So based on the formula, we can write it to be ABC times X minus X0, Y minus Y0, Z minus Z0, all in bracket equals 0. Or we can write it to be A times X minus X0 all in bracket plus Z times Y minus Y0 all in bracket times C plus C times Z minus Z0 all in bracket equals 0. So the formula is proven, and it will be the same if we will prove the formula on the line.
The next topic is will be back explained by Abdul Furqan. This topic is orthogonal projection. To Abdul Furqan, time is yours.
The next topic is orthogonal projections. Orthogonal projections, in many applications, it is necessary to decompose a vector U into a sum of two terms. One term being a scalar multiple of a specified non-zero vector A, and the other term being orthogonal to A. For example, if U and A are vectors in two-dimensional space that are positioned so their initial points coincide at a point P, then we can create such a decomposition as follows in figure 3.3.2. Since W1 plus W2 equals W1 plus U minus W1 all in brackets equals U, we have decomposed U into a sum of two orthogonal vectors that the first term being a scalar multiple of A and the second being orthogonal to A. The following theorem shows that the foregoing results, which we will illustrate using vectors in two-dimensional space, apply as well in n-dimensional space. Projection theorem. If U and A are vectors in n-dimensional space, and if A not equal 0, then U can be expressed in exactly one way in the form U equals W1 plus W2, where W1 is the scalar multiple of A and W2 is orthogonal to A. So the proof, since the vector W1 is to be a scalar multiple of A, it must have the form W1 equals K times A. Our goal is to find a value of scalar K and a vector W2 that is orthogonal to A, such that U equals W1 plus W2. We can determine K by using equation 7 to rewrite equation 8 as U equals W1 plus W2 equals K A plus W2. And then applying the theorems. To obtain u dot a equals ka plus w2 all in brackets times a equals k, the length of a squared plus w2 times a all in bracket. Since w2 is to be orthogonal to a, the last term in equation 9 must be 0, and hence k must satisfy the equations u dot a equals k, the length of a squared, from which we obtain k equals u dot a over the length of a squared. As the only possible value for k, the proof can be complete by rewriting equation 8 as w2 equals u minus w1 equals u minus ka equals u minus u dot a over the length of a squared times a. The vectors w1 and w2 in the projection theorems have associated names. The vector w1 is called the orthogonal projection of u on a, or sometimes the vector component of u along a. And the vector w2 is called the vector component of u orthogonal to a. The vector w1 is commonly denoted by the symbol projection u to a, in which case it follows from equation 8 that w2 equals u minus projection u to a. In summary, projection u to a equals u times a over the length of a squared times a. That is vector component of u along a. U minus projection u to a equals u minus u dot a over the length of a squared times a, vector component of u orthogonal to a. For the example, vector component of u along a, let u equals 2, minus 1 and 3, and a equals 4, minus 1 and 2. Find the vector component of u along a and the vector component of u orthogonal to a. So the solution, u dot a is equals 2 times 4 plus minus 1 times minus 1 plus 3 times 2. That is equals to 15. And the length of a squared is 4 squared plus minus 1 squared plus 2 squared is equals to 21. Thus the vector component of u along a is projection u to a equals u times u dot a over the length of a squared times a equals 15 over 21 times 4 minus 1 2 equals to 20 over 7 minus 5 over 7 and 10 over 7. And the vector component of u orthogonal to a is u minus projection u to a equals 2 minus 1 and 3. We subtract it by 20 over 7 minus negative 5 over 7 and 10 over 7. It equals negative 7 over and negative 6 over 7, negative 2 over 7 and 11 over 7. Sometimes we will be more interested in the norm of the vector component of u along a than in the vector component itself. A formula for this norm can be derived as follows. The length of projection u to a equals the length of u times a over the length of a squared times a equals the absolute value of u times a over the length of a squared times the length of a equals absolute value of u times dot a over the length of a squared times a times the length of a, where the second equality follows from part C of the theorem and the third from the fact that the length of A squared is more than 0. Thus, the length of projection U to A equals absolute value of U dot A over the length of A. If theta denotes the angle between U and A, then U dot A equals the length of U times the length of A cos theta. So the equation 12 can also be written as the length of projection U to A equals the length of U times absolute value of cos theta.
The next topic will be explained with Puja Islami Putri. This topic is the theorem of Pythagoras. To Puja Islami Putri, time is yours.
Okay, the next material is about the theorem of Pythagoras. Theorem of Pythagoras in n-dimensional space. If U and V are orthogonal vectors in n-dimensional space with the equation in a product, then the length of U plus V squared is equal to the length of U squared plus the length of V squared. Now we will prove whether the length of U plus V squared is the same as the length of U squared plus the length of V squared. The length of U plus V squared is equal to U plus V all bracket squared. U plus V all in bracket square is equal to U plus V all in bracket times U plus V all in bracket equals U squared plus UV plus UV plus V squared equals U squared plus U times 2 times U times V plus V squared. Since U and V are orthogonal, we have U dot V equals 0. Then U plus V all bracket square is equal to U squared plus V squared. So the length of U plus V squared equals to the length of U squared plus the length of V squared. So the formula is proven. For example, we show in example orthogonal vector U negative 2, 3, 1, 4 and V 1, 2, 0, negative 1 are orthogonal. Verify the theorem of Pythagoras for these vectors. Okay, so in this example, we can write that U plus V equals negative 2, 3, 1, and 4 plus 1, 2, 0, negative 1. And we got the result is negative 1, 5, 1, and 3. And then we can write U plus V on bracket square is equal to negative 1, 5, 1, 3 times negative 1, 5, 1 and 3. And the result is 1 plus 15 plus 1 plus 9. So the length of U plus V squared is equal to 36.
Next will be the last topic is distance problem will be explained with me, Nurlaila Ramadhani. To me, time is yours. In this section, I will be explain about distance problems. In distance problems, there are theorems 3.3.4. This theorem is in two-dimensional space, the distance d between the point P0, x0, y0 and the line ax plus bx plus c equals 0 is d equals absolute value of a times x0 plus b times y0 plus c over square root of a squared plus b squared. The underlying idea of the proof is illustrated in a figure 3.3.6. As shown in the figure, let Q, x1, y1 be any point in the plane and let n, a equals a, b be a normal vector to the plane that is positioned with its initial point at P. It is now evident that the distance d between P0 and the plane is simply the length or norm of the orthogonal projection of the vector P0 on N, which by formula is the length of projection P0 to N equals absolute value of the vector P0 times N over the length of N. So we find each value of the formula. The vector of P0 equals x0 minus x1, y0 minus y1, and then the vector of P0 times N equals a times x0 minus x1 all in bracket plus b times y0 minus y1 all in bracket. And then we know that the length of N equals the square root of a squared plus b squared. We can substitute all the values that we have before to the formula. D equals the length of projection, the vector of P0 to the N equals the absolute value, the vector of P0 times N over the length of N equals, and then we can substitute all the value, the length of A times x0 minus x1 all in bracket plus b times x0 minus y1 all in bracket over the square root of a squared plus b squared. We can simplify the formula. The formula will be equals the absolute value of a times x0 minus a times x1 plus b times y0 minus b times y1 over the square root of a squared plus b squared. Since the point P, x1, y1 lies in the given plane, its coordinates satisfy the equation of that plane. Thus, a x1 plus b y1 plus c equals 0. So we can find the c. C equals minus a x1 minus b y1. So this c will be the one equation, or we call this one equation. So we substituting one equation that to the formula. So the d equals the length of projection, the vector of P0 to the N equals the absolute value of a x0 minus a x1 plus b y0 minus b y1 over square root of a squared plus b squared. So we can simplify, or we know that c is minus a x1 minus b y1. So we can substitute, and then we find the absolute value a x0 plus b y0 plus c over the square root of a squared plus b squared is proven or proved. And then the second theorem in theorem 3.3.4 is in three-dimensional space, the distance d between the point P0, x0, y0, z0 and the plane ax plus by plus cz plus d equals to 0 is d equals absolute value of A times x0 plus B times y0 plus C times z0 plus D over square root of a squared plus b squared plus c squared. So we have to prove this theorem. Prove this theorem with the underlying idea of the proof is illustrated in figure 3.3.6. As shown in that figure, let P x1, y1, z1 be any point in the plane, and let n, a, b, c be a normal vector to the plane that is positioned with its initial point at P. So it's now evident that the distance d between P0 and the plane is simplified the length or norm of the orthogonal projection of the vector of P0 on n, which by formula is d, the length of projection vector P0 to n, equals the absolute value of vector P0 times n over the length of n. So we have to find the each value of that formula. The vector of P0 equals x0 minus x1, y0 minus y1, z0 minus z1, all in bracket. So we know that the vector of P0 times n equals to a times x0 minus x1 all in bracket plus b times y0 minus y1 all in bracket plus c times z0 minus z1 all in bracket. And then we have to find that the length of n. The length of n equals the square root of a squared plus b squared plus c squared. And then that value we can substitute to the formula. D equals the absolute value of a times x0 minus x1 plus b times y0 minus y1 plus c times z0 minus z1 over square root of a squared plus b squared plus c squared. Since the point key x1, y1, z1 lies in the given plane, if the coordinates satisfy the equation of that plane, thus a x1 plus b y1 plus c z1 plus d equals 0. So we can find the d equals minus a x1 minus b by minus c z1. Okay, next will be the section of example. Okay, this example is distance between a point and a plane. So the problem is find the distance d between the point 1, -4, -3 and the plane 2x minus 3y plus 6z equals -1. Now, the solution is, since the distance formula in theorem 3.3.4 requires that the equation of the line and the plane be written with 0 on the right side, we first need to rewrite the equation of the plane as 2x minus 3y plus 6z plus 1 equals to 0. So we can know that A, B, C, and then x0, y0, c0, and d. So we can substitute that value of the formula. And then we have d equals, and then we, after. And then, ini jelas loh Laila. the absolute value of 2 times 1 plus negative 3 times negative 4 plus 6 times negative 3 plus 1 over the square root of 2 squared plus negative 3 squared plus 6 squared. And then we can simplify this equation to the absolute value of minus 3 over 7. And then we find the D with 3 over 7. That's all from us. Explain about point multiplication and production of factor. Hope you can enjoy this video and understand what we talking about. And then see you next time. Thank you for attention. Assalamualaikum warahmatullahi wabarakatuh.